The 1910 Nobel Prize in Physics went to this guy, Johannes Diderik van der Waals. He was a Dutch theoretical physicist who became kind of famous for his work on the equation state of gases and liquids. In fact, that's exactly what he won the prize for. But that's really kind of just a really complicated way of saying we kind of owe this guy the sort of modern way of life when it comes to understanding how certain conveniences work. And without his theoretical, weird mathematical stuff, we wouldn't be able to build things really, really efficiently that we've all come to know and love. So he worked on a bunch of equations, and he was trying to figure out a way to accurately describe gas inside a container and what happens to that gas as you change the physical conditions of that chamber, whether that's changes in the volume or the pressure or other things. And what he came up with was an equation that in and of itself was a little bit different than what is typically used, but it ends up in this thing called the ideal gas law, which is essentially pressure times the volume is equal to the amount of a substance times the ideal gas constant, which is the product of Boltzmann's and Avogadro's constants, times the temperature. So if you raise the temperature and you keep the volume the same, the pressure goes up. If you pressurize it and you change the volume a little bit or put it under higher pressure, this equation must stay balanced. So when you change one of those conditions, the mass must stay the same. The left side must always equal to the right side. So if you change the pressure, you change the volume, you change the temperature, or you change the amount of a substance, the other side of that equal sign must change appropriately. Now, technically, the internal combustion engine does predate his work by about 20 years. But at the time, those engines were very faulty. They broke down all the time. They're incredibly inefficient. But everybody saw the promise. Now, when van der Waals comes along with his work in 1873 and accurately defines the behavior of gases in different situations, the internal combustion engine starts to make giant leaps in its utility. So what you'll find inside those engines is you have pistons, and when the piston is smaller, in other words, the piston head is up at the top, fuel is injected, it is set fire, and it shoves that piston down to the bottom, changing the volume. But in the process, what it does is it turns a crankshaft, it turns things in the motor, and eventually transitions that energy over to the wheels and makes the car move forward. But if we didn't fully understand that behavior of gases at different temperatures and different pressures and different volumes and how they would result in the forces being applied to that piston head, none of those things would be as nearly as efficient as they are today. So when you buy a modern engine and you realize, well, gee, I'm getting a lot more horsepower for the size engine that I got, even back in the 1980s and 1990s, it's because we're still refining just how well you can make those things, and it is all based on the ideal gas law. Now, van der Waals did a great number of other things besides just the ideal gas law, including modern theories of intermolecular forces, corresponding states of the real gas law, van der Waals forces, the equation of state, the van der Waals radius, van der Waals surface, the van der Waals molecule. The list goes on. And many of his things are still used in labs all over the world today. They're used by engineers everywhere. But as I'm recording this video in August in Texas, my favorite invention right now that the ideal gas law happens to apply to is air conditioning. Inside your air conditioner, there's a gas called Freon. There's also a compressor. And as you change the conditions inside that compressor, where you expand the volume or reduce the volume or move it around, what you're going to do is change the temperature of that gas. And as that gas changes, it's blown into your house and you get cool air. All because van der Waals fully figured out exactly what's going on down at the molecular level with gases, both in their gaseous state and as they transition over to liquid. So we have this man to thank for his work on a chalkboard, coming up with lots of equations to explain the behavior of other people's experiments when we look at far more efficient cars and we look at more efficient air conditioning. We have this guy to thank. So I hope everybody's enjoyed this particular one. Don't forget to hit subscribe, and we will see you on the next video.